Welcome to Radiation Information for Everyone, online short courses on radiation, biology, and society. This is one of two presentations that I've created for the third session of the class, Disproportionate Impacts of Ionizing Radiation, and I'm Cindy Folkers of Beyond Nuclear. In the presentation Nuclear Sacrifices, I walked through some of the political and societal hypocrisies that were committed by people in government and industry in order to ensure that nuclear technology was supported. Now, the decisions that they made, despite the evidence that was facing them, are still impacting us negatively today. In this presentation, I share how government and industry support for nuclear technology has obscured the science that reveals disproportionate impacts of radiation exposure on pregnancy, children, and future life. So let's start with some basic science of radiation damage. Four main things can happen to a single cell once it is hit by any type of ionizing radiation. The cell can be undamaged or damage and properly repair. The cell can be so damaged that it dies. The cell can be damaged, improperly repair, live and reproduce, but the daughter cells die. And finally, the cell can be damaged, look repaired, but it holds mutations that it passes on to daughter cells, which in turn are mutated and survive. Now, for lower doses especially, this is the important process because it can result in diseases that can show up in humans and other animals decades or even generations after the initial damage. How much damage a hit by radiation will cause is variable due to many factors, including the age of the person, the difference between people's ability to repair themselves, and the difference between certain types of cells. The type of radiation also matters, as well as the type of exposure. So there are many different types of cells within the individual that perform specific functions. For instance, brain cells are different from nerve cells, which are different from heart muscle cells, and so on. Some cells are more radiosensitive than other ones, such as bone marrow and stem cells. Finally, studies show that children, women, and pregnancy are more susceptible to the effects of radiation. That means they're more likely to get diseases from exposure to it than the male standard that we're currently using as the basis for our radiation exposure standards. And these disproportionate impacts are my focus. To that end, let's look at where some radioisotopes travel and collect in the pregnant body. Now, this graphic does not contain all radionuclides. For instance, routinely released noble gases are not represented in this graphic. But what I would point out from this graphic is the collection in the fetus of nearly every radionuclide listed here. And do note that radioactive carbon and radioactive hydrogen, known as tritium, can collect in fetal tissue at twice the concentration as they do in maternal tissue. And they are basic building blocks of the human body, so this is no surprise, as is calcium, which is mimicked by radioactive strontium, which is a bone seeker that lodges in the mineral bone of growing skeletons and likely won't leave for most of that person's life. So how can we determine how damaging a specific radioisotope is for any given organ? Well, we need to convert from how radioactive something is, and that's in a unit called a becquerel, to the kind of damage that it causes in a unit called sieverts. And this is the formula that does that. This is their basic attempt to calculate and to help us understand how much and what kind of biological damage comes from exposure to different kinds of radioisotopes and the kinds of radiation they give off. Now, this formula encompasses individual nuclides that are deposited in the body, so this would be for internal doses. There are also biokinetic models describing basically where in the body the radionuclide goes and when or if it ever leaves. But the basis for these models has mostly been higher doses, mostly representative of a male adult. For low dose dosimetry, chronic and internal exposures, these models are lacking, as the intricacies and individualities of a fully functioning human system are largely avoided in these models. Adults, for instance, are represented as slabs of meat. That's my characterization because they are not reflective of the complexities of damage. Cumulative damage by continuing exposure is not accounted for. Neither are metabolic or hormone pathways, particularly the estrogenic pathway, which does seem susceptible to action by ionizing radiation. Biokinetic models are not sex-specific. A male model is still used for females, and they are also not age-dependent. In general, these formulas represent transport systems, but there are many more systems in our bodies, one of which is the reproductive system. And although they are in process, the people who recommend exposure standards, the officials, the experts, are in process of correcting for some of these shortcomings. We have a whole body of studies that have made poor assumptions about dose impacts to date, particularly from recurring lower doses, both internal and external, although we do focus here in this presentation more on internal doses. Unfortunately, the poor assumptions have quote-unquote scooped the narrative about what the damage is or is expected to be without coming clean on the depth and the importance of the uncertainties, and as such, we are stuck with preconceived notions that allow nuclear technology advocates to ignore, in certain instances, what actual science and the lived experiences of people are telling us. So let's review in more detail some of these shortcomings, uncertainties, and the impacts specifically on protection of pregnancy and future generations. Many of the underlying assumptions for these shortcomings come from the International Commission on Radiological Protection, or ICRP for short. That's an organization that self-declares its expertise on radiation and that establishes recommendations for radiation exposure, often used by national and state governments. The ICRP recommendations do fail to account for several significant developments during pregnancy, a fact that ICRP, to its credit, does often recognize. That doesn't seem to stop anyone, though, from pursuing nuclear technology. This is Lauriston Taylor. Lauriston Taylor believed low doses were not harmful. He was responsible for establishing committees of the ICRP to set permissible doses. Doses not based on precaution. Through the use of a permissible dose, sacrifice of human health was programmed into the ICRP recommendations. And ICRP's task is still to optimize radiation exposure, not by minimizing dose, but rather by limiting, quote, detrimental effects of radiation exposure without unduly limiting desirable human actions. The definition here of detrimental being open to a wide interpretation, of course. Unsurprisingly, then, ICRP concludes that in emergency and existing exposure situations, quote, prenatal exposure would not be a specific protection case, i.e., would not require protective actions other than those aimed at the general population. By comparison, Environmental Protection Agency recommendations have a risk factor that is increased by 10 for just after birth and before the age of 2. For some of the toxins that they regulate. So we start to see the preferential treatment radiation receives, and while it is true that the EPA recommendations are not for pregnancy, development during pregnancy is uniquely susceptible to damage, so even the EPA's factor of a 10 in increased risk for post-birth would not be protective enough for pregnancy development. Meanwhile, ICRP sees no need for addressing these unique sensitivities during pregnancy as a specific protection case. As such, we see assumptions discounting prenatal exposure woven throughout ICRP recommendations, and we're going to review those in a minute, but first it would help here to review the stages of pregnancy development itself. Now, development during pregnancy is approximate, and the starred items in this chart, which represents the most vulnerable times of the fetus and the embryo for the vulnerable organ development at that time didn't really have represented some of the developments that I thought were also very important for ionizing radiation exposure. I have added those developments along with their approximate developmental times during pregnancy down here. The ones that I noted are denoted by stars, and they do not have the vulnerability times represented as the rest of this chart does for these other organ development times, because I simply do not know. I regard all of pregnancy development as different times of vulnerability happening at different parts of pregnancy development, as this chart actually does demonstrate. Also, please note that this chart is used by people concerned with and trying to prevent fetal alcohol syndrome, but this chart is not specific to fetal alcohol syndromes, as the vulnerability time periods that are represented here are specific to the development of pregnancy outside of any concern of just fetal alcohol syndrome. And also do note that the pregnancy loss time frame here can occur in a time period where a woman might not know that she is pregnant. So most organs begin to form at about 3 weeks after fertilization. The heart and major blood vessels begin to develop a little earlier, by about day 16. Shortly thereafter, the area that will become the brain and the spinal cord, neural tube, begin to develop and will continue to develop throughout the pregnancy. The heart begins to pump fluid through blood vessels by about day 20. Blood vessels continue to develop in the embryo and the placenta at that point. Most malformations or birth defects occur during the period when the organs are forming. At the end of about the 8th week after fertilization, the embryo is considered a fetus, and we can see that represented here in this chart. During this stage, the structures that have already formed continue to grow and develop. The lungs continue to mature until near the time of delivery. The brain accumulates new cells throughout the pregnancy and the first year of life after birth. Approximately 7 to 20 weeks is the differentiation of the sex between the male and female, and this is important because that's the subsequent development of the female reproductive system, including the ovaries, or the beginnings of the ovaries, and the eggs. The placenta starts developing very early on in the pregnancy, at about when the embryo implants into the wall of the uterus. And over the next 2 months, the placenta continues to develop. Between weeks 8 to 12, the placenta takes over from a structure called the corpus luteum, and it'll sustain the fetus for the rest of the pregnancy once the placenta does this, and continue to grow larger as the fetus grows. For most of the first trimester, the corpus luteum, which was a collection of cells, performs the placenta's essential functions. It produces progesterone and estrogen while the placenta forms. And the placental formation is extremely important because the ICRP really does discount the placental function as an organ. During the first trimester, the bones begin to develop, replacing the cartilage that has already mapped out the entire skeleton. And the bone continues to grow throughout the rest of the pregnancy. Blood cell development begins as early as the 7th day of embryonic life, and at 20 weeks, it starts to colonize the bone marrow. The development and changes continue even up to 32 weeks of pregnancy. Now, here's why pregnancy development timing is so important when assessing radiation damage. Stochastic health impacts. That includes cancer and other genetic damage. They represent one major category of uncertainty in radiation exposure. Stochastic damage is, by definition, random, and therefore difficult to predict and protect against. Now, ICRP does try to attain a, quote, reasonably achievable, end quote, protection against these impacts, the severity of which is ostensibly independent of dose and without threshold. As population exposures increase, though, through unrecognized contamination in food, water, air, and soil, the number of people exposed to radiation will increase, and the number of people will affected will therefore increase. So even decades later, as an example, the cesium-137 that was released from the atomic bomb explosions and also civilian nuclear routine releases and catastrophes is impossible to avoid, according to the Environmental Protection Agency. And radiostrontium and plutonium still appear in children's teeth decades after above-ground bomb tests. Protecting pregnancy development from stochastic damage, where one hit from radiation could destroy or damage the cells meant to become an organ, like the brain or the heart, will become more challenging, especially as fetal tissue collects some regularly released radionuclides, as we've pointed out before, like carbon-14 and tritium, at nearly twice the concentration that the maternal tissue collects it. Now, this graphic is a very basic representation of normal human hematopoiesis or blood cell formation, which occurs in our bone marrow. While ICRP claims that lifetime cancer risk following in utero exposure will be similar to exposure risk in early childhood, at the same time, they admit they fail to account for damage to all the highly sensitive prototissue or organ-forming sites and stem cells responsible for blood formation. In fact, hematopoietic tissues appear more radiosensitive in embryos and fetuses than in newborns, not really a surprise. So comparison of in utero exposure risk to early childhood risk is really not viable. And to put this in the context of EPA's times 10 increased risk for newborns, noting that for blood-forming tissue damage in utero, this increased risk factor is still not high enough. As we are seeing, damage to a number of processes during pregnancy are either poorly accounted for or not accounted for at all, including damage to sites and stem cells responsible for blood formation, as we just discussed, but also the maternal exchange system, and embryo organ tissues and placental function, which are poorly represented. Now, I've included the embryo damage window part of the chart from slide 7, from approximately weeks 3 to 8. And this is to remind you of approximately what developments are taking place during this time frame. ICRP uses dose to the uterus to approximate dose to the embryo, which they define as conception to day 56, which is about the end of week 8. Therefore, ICRP claims all embryonic tissues receive the same dose. This might be defensible for external doses. Maybe. I could see that argument being made, not that I would agree, but internal doses are a different matter. And in fact, ICRP does recognize the shortcoming of this approach, saying that averaging of dose over the uterus, quote, hides the fact that the very early embryo with a small number of cells might receive doses significantly higher or lower than this average. However, ICRP maintains that future developments can correct for this. Well, we are over 100 years into the nuclear age, still waiting on those future developments to correct for this. Children are represented as little adults, and damage to children's organs are based almost exclusively on weight, not function or dysfunction of organs or bodily functions over time. ICRP uses models made for postnatal exposures to calculate radiation damage to prenatal tissues and organs, and mentions the shortcomings of this approach, but it claims there is a lack of data about damage at these early life stages, and that using this method makes it more convenient for comparing dose data with adults. It is unclear what they think is comparable between a fully formed adult and an embryo fetus developing from a system that is unique in form and function, and particularly susceptible to damage. While ICRP at least admits shortcomings in other areas of pregnancy protection, it seems blind to the unique role of the placenta, recognizing it as a conduit for toxins, yes, like radionuclides and nutrients, but implying that only its mass matters. In reality, the placenta is a fully functioning ad hoc organ developing during pregnancy, subject to damage to its functions from radioactivity. It supplies oxygen, removes metabolic products, and provides a limited barrier against toxins and drugs. It is active endocrinologically to support the ongoing pregnancy. So radiation radiation exposure could damage not only the fetal cells, but also impairs placental development and function by cell killing and cell cycle arrest. Improper placental formation or function can result in low or high birth weight for babies, which in turn seems connected to negative impacts later in adult life. ICRP does not attempt to have specific recommendations protecting female fetuses, which develop all of their eggs or egg precursors during prenatal growth. Not only the developing fetus, but also the fetus's future children, therefore, could be at risk from radiation exposure, and Dr. Arjun Makhijani has promoted using the reference embryo or reference fetus as a model for radiation protection. Very wise. Since the sex of a fetus is often difficult to determine until about the 18th week of pregnancy or later, this standard would protect all early pregnancy at the most protective level, as if all fetuses were female. ICRP does not account for cumulative biological damage to an individual from continuing exposure to low doses, nor does it believe it has enough information to calculate cumulative heritable radiation damage past the second generation. ICRP correctly reasons that the estimates used for the cumulative generational risk equation may not remain valid for hundreds of human generations, but this uncertainty has not halted nuclear technology development. For the generational impact that ICRP does calculate, the second exposed generation has more genetic diseases than the first for the same dose to each generation. And research does indicate that the ability to cope with low-dose chronic radiation exposure will decrease over generations, supporting ICRP's modeled trajectory of increasing vulnerability to genetic weakening and disease causation over the 2 generations ICRP does model. Speaking of research, we should now review what studies are actually showing. Continuing exposure to radiation levels at or near natural background doses are associated with increases in childhood cancer, primarily central nervous system cancers and leukemias. And you can see this represented here in these 2 graphs on this slide. For reference, naturally occurring background radiation exposure average is about 0.8 to 1 millisievert, that's about 100 millirem, without radon, which is mitigable and which not everyone is exposed to per year. And note that at 225 nanosieverts, which is about here in this graph, that's about 1.97 millisieverts per year, at which the exposed individual would have twice the chance of developing the disease. Dozens of studies show increases of childhood leukemia around normally operating nuclear facilities, particularly in children under 5 years of age. There were increases of childhood leukemia in children who resided within 5 kilometers downwind of the Krimmel boiling water reactor. That's represented here by this map. Following this study and others like it, the German government funded a countrywide study which showed that children under 5 living within 5 kilometers of reactors in Germany had elevated rates of leukemia. A cascade of studies followed in other European countries. They showed much the same result, and you can see these data pooled here in this table, which was the data being compiled by Alfred Körblein and Ian Fairley. We have independent studies in the U.S. showing increases as well, but we have yet to have an official U.S.-wide study undertaken on this critical issue of childhood cancers around nuclear facilities. Dr. Ian Fairley's theory is that the observed high rates of infant leukemias may be a teratogenic effect from radionuclides incorporated during pregnancy, end quote. where teratogenic is defined as physical or functional defects in the human embryo or fetus after the pregnant woman is exposed to the substance. Research was just released, by the way, noting that there seems to be a global epidemic of cancer in people under 50. This is something that we have not experienced before. Recent study on perinatal mortality in Japan following the Fukushima meltdown and explosion in March 2011 shows that during the 2012 to 2019 time period, there were 590 excess perinatal deaths in the area shown here in dark and light gray. Further, there were massive increases in 2018 and 2019 in the 4 core prefectures represented here in the areas in dark gray, meaning that this issue continued past the initial plume exposures and therefore could be pointing to ongoing radioactive contamination as partly responsible for these increases. The study recommends continued investigation of perinatal mortality in contaminated regions of Japan. And I should note here, if radiation is ending pregnancies early, some may be ending before a woman knows that she's pregnant, and this would manifest in a decrease in fertility. A recent report by the National Academy of Sciences on the future of low-dose radiation research mentions, quote, a study that found exposure during the first trimester to cosmic radiation as low as 0.36 millisieverts may be linked to increased risk of miscarriage. After living with Chernobyl contamination for decades, studies indicate radiation damage may be carried and compounded across generations, and a recent study in the Bryansk region of Russia, the Bryansk region being inside this green circle, it associates birth defects with living in contaminated areas. Now, some of these birth defects are de novo, meaning that they are appearing in this population for the very first time. Further study projections indicate that certain birth defects will continue to increase here in the next few years. The NAS report on low doses states that, quote, cancer is the health outcome most commonly studied for its association with low doses of radiation, and heritable genetic effects are assumed to be associated with low-dose exposures, despite minimal evidence to date of such effects in humans. But I would argue studies like the Bryansk study indicate that humans are not immune to heritable effects, and it is unclear how these studies are accounting for pregnancy terminations after the mother receives a medical diagnosis of birth defects while the fetus is in utero. Again, impact on pregnancies may show up in the data as inability to conceive also, rather than clinically diagnosable conditions like miscarriage or perinatal mortality. There is increasing evidence that low doses may cause non-cancer health outcomes, including cardiovascular disease, neurological disorder, immune dysfunction, and cataracts, again according to the recent NAS report. Radioactivity in air pollution is now also linked by a recent study with cardiovascular harm. Post-Chernobyl studies of regions outside the former Soviet Union point to more subtle cognitive impact among children, subclinical outcomes not readily associated with radiation exposure, and yet, in Nordic countries, children exposed to in utero to higher Chernobyl fallout performed worse in secondary school, particularly in math. They presented more behavioral problems, had significantly lower verbal IQ, verbal working memory, and executive functioning. These researchers estimate that the highest doses received was 4 millisievert. Further, the NAS report, which I've been quoting from states that acute or low chronic doses, quote, indicate a pro-inflammatory immune profile, which might contribute to chronic immune dysfunction and disease, end quote, and can change immune system balance to provide the framework for induction of symptomatic immune dysfunctions that are clinically relevant, such as infections, allergies, autoimmunity, and immunoproliferative diseases. Now, autoimmune diseases like chronic fatigue immune dysfunction syndrome, known as CFIDS for short, are much more prevalent among women than men, meaning that if radiation is implicated in causing these syndromes, it could be, by definition, disproportionately impacting females, since they already represent an overwhelming number of autoimmune disease cases. Such a disproportionate impact exists in the atomic bomb data for women and cancer. This graph represents CFS cases, and it shows that CFS is higher in women for all ages than men. In fact, of the 8.5 million people with autoimmune diseases, 80% are women. And we aren't just exposed to radioactivity. Complex environmental exposures from a variety of sources like chemicals, infectious agents, lifestyle factors, and how they can affect a person's health during their lifetime is called the exposome. Now, the study by Korsakov that I mentioned earlier that was in the Bryansk region of Russia also uniquely examined and demonstrated additive and potentially synergistic impacts in areas contaminated by Chernobyl radioactivity and industrial chemicals. And many marginalized communities are exposed to more than one industrial toxin, and radioactivity can be a significant part of this toxic stew. So the way that the exposome model investigates health damage is novel and would bring a fresh approach to radiation damage research. ICRP has never accounted for greater damage on women, children, and pregnancy development in a full or robust capacity, choosing to move ahead instead with nuclear tech development. Now, when ICRP does make updates to its model assumptions, it can take 20 to 40 years to actually have these changes reflected in the regulations, if ever. So when they say they are waiting on future developments to clarify the science, don't hold your breath. And children are not a subpopulation. They are everyone. No one gets here without a pregnancy, and damage is happening during pregnancy that can not only affect us in childhood, but for the rest of our lives and across generations. So really, what is at stake through our determined use of nuclear technology, despite the health research and what it is showing, and what our lived experiences are, and what uncertainties remain? Our genetic viability, our ability to have healthy pregnancy outcomes, and live healthy lives. Here's a list of resources that I've used to create this presentation. This is the first slide of them, and this is the second slide. And thank you so much for your attention.